Let's talk together and we'll recap a bit about Kepler's laws and talk about the reading assignment for today as well. So, well, let's just look back at the first of the labs, Lab A. And the big idea there was, at the very end, it asks, what is Kepler's first law of planetary motion? This is in real time right now. This is actually happening. There's muttering. There's much rifling through papers. Yes, David. Yeah, what is it?
R equals P over 1 plus E plus 1.
Give me that again.
R equals P.
Son of a gun.
Trick question, they weren't laws, there were suggestions.
This is funny right here.
You don't have an ink color selected.
Trick question. Dr. Wigisari is acting
Okay. Can I do it now? No. R equals
P over 1 plus E cosine theta.
okay. Well, what does that mean?
I don't know.
So there are word definitions that are easier to understand.
Wasn't it that all planets orbit around the sun in elliptical orbits and the sun is one foci?
Right. So every stable orbit is an ellipse, and the sun is at one focus. So what that means, going back here to this page, whenever you've got a conic section, you can measure the eccentricity of it. We're not going to go into that. The formula that you gave me measures that. It's in polar coordinates, which instead of x and y tells us what angle and how far out. So theta and r. Yeah.
You might have misread the reading, but it said that like a planet can travel in like hyperbole.
Hyperbola.
How does that?
So here's what happens. A stable orbit, the ones that Kepler was observing, are all ellipses, which include potentially circles depending on the eccentricity. So at one end, if you've got an eccentricity of 0, that means a circle. So eccentricity is a measure of the sort of the semi-major axis. Let's see if I can do this. And the semi-minor axis. So, no. Oh, I'm hating it. I had some computer trouble over the weekend, and it seems to have bled in. And I don't think it's going to let me do this.
Try the ground.
Pick it up and try it. Now set it back down. Now it'll let you. Oh,
Try.
Nice work, Troy.
I might abandon
You observed what I was doing, what happened last time. Anyway,
We're in the winch.
so whatever happened, so the semi-major axis, the one out towards the long one, and the semi-minor axis. And so if those two are equal, we have a circle. And so it's just the same radius around. But then as eccentricity goes up from 0, it gets longer and longer until eccentricity of just under 1. All of those are ellipses. Any of them are allowable for a stable orbit. The focus is a point, it would be if we had a perfect circle, it'd be right in the center, but it's a point off to the side here, and then there'd be another focus spaced out. You can think of this, if you ever want to draw an ellipse, you set these two foci, put them in with pins or something, tie a string around each one, and have lots of extra string. Then if you put your pen and stretch the string out, you'll be able to go around it by stretching that string out and draw your ellipse. So you can kind of think of it that way. The foci are the two sort of anchors. However, other orbits, which aren't maybe still orbits, but if some two things are passing each other with gravity pulling them together, other paths are allowable. And it would depend on the eccentricity. So if we have an eccentricity of 1, what do we have? What is this shape? Parabola. If it's more than 1, now we have your hyperbole. Super hyperbola. See what I did there? All of these are allowable, but this would be more the case of a planet comes in from the outside. The star would be here, and it zips off into space. So it's redirected by the planet. We see this with like the slingshot sort of stuff with satellites and things that we're sending out. We use that, and you can use the hyperbola, anything like that. So above 1 is a parabola, above 1 is a hyperbola, and all of those are ways that a gravity can affect things. Now the reading question related to that a lot of people have asked, it says, one focus of Earth's elliptical orbit is near the center of the sun. How far away from the sun is the second focus? And so I've drawn a slightly exaggerated, fairly round, but let's pretend that Earth is on the orbit and we've got the sun here in one focus, which would be about right here. But then there'd be another focus here. And I am intentionally exaggerating that a bit. How far away is it? Well, this is the closest the Earth ever gets to the sun. What do we call that? Perihelion. This, then, since the sun is not moving to the other focus, is the farthest Earth is ever going to get from the sun. What do we call that? Aphelion. I remember those because aphelion starts with A, just like away does. So it's farthest away. If we look at this, the distance between the Earth and that should also be the same distance as a perihelion. Even though it's not technically the perihelion because it's not related to the sun, which is where we get the helium. And so if you take the difference of these two, you find the distance from the one focus to the other in this. I don't remember what that value ends up being, but it gives you an idea. And the more elliptical these orbits, the farther that's going to be. Pluto has quite an elliptical orbit, for example, and so it's going to be much greater. Mm-hmm.
Is the second focus important at all?
Not astronomically. There's nothing technically there. It would just be empty space. It's important mathematically for the shape, but otherwise not really. If we had two bodies that were of equivalent mass, then both of them would be much more important. They'd be orbiting around those 2 points, essentially. Johannes Kepler was a mathematician more than an astronomer, so how did he come up with those groovy laws? What's the history on that? He didn't do the observations.
We did the observations and then paid Kepler to make sense of them.
Yeah. What was that other dude? Said some dude? Tycho Brahe. I don't know. Does anyone choose Tycho Brahe for a presentation? No? Then I'll reveal some. He was very interesting. He was missing a good chunk of his nose because he lost it in a pistol duel. He had a new one made out of gold. I think it was gold. Might have been lead, but I think it was gold. He was a Dane, and he was highly respected, so he had his own lands and maybe his own island, I don't even know. And he would throw raucous parties. Parties So raucous that his pet moose once got so drunk it fell down the stairs. I don't know. And he kept a little person as his fool to amuse him whenever he wanted to be amused. What's that? a little Sancho Panza, but perhaps, well, with enough sense to, I guess, get paid to act like a fool. So that's not all bad. So he was an interesting character. So if someone's still there, we have 5 or 6 people still looking for topics. That might be a good one. He was quite a character and a heck of an astronomer. And then finally, so related to this, from Kepler's finding, what shape of orbits are allowable by nature? So ellipses for sure. I'm not sure if we'd call the rest of these orbits or not. They're certainly allowable based on how things would travel, but an orbit, you might argue, has to keep going around, or it's not an orbit anymore. So that would be ellipses or circle at one extreme. Okay. Let's look at Lab B, second law. What is Kepler's second law state? This isn't going to work either, but okay, so what is Newton's second law state?
Newton's second law is force equals mass times acceleration.
Kepler's. Yes, a couple people got me there. Kepler's second law. What does that state? Yeah.
During the same amount of time, the area will be the same.
Area of what?
This,
So let's exaggerate this. Let's put the focus way over there. If we have 30 days, say from those 2 points, 30 days from between these 2 points, the areas in here will be the same. So the same amount of time, what is the word? Scribes out the same area within the ellipse. Now, when the planet or whatever is closest to its orbiting body, so the sun here, it has to go faster. Otherwise, it's going to be pulled in because the force here is greater. So we've always got the force G m1, whatever it's orbiting, and times m2, the object itself, over the square of the distance between them. So that as this distance gets smaller, the force gets greater and it's pulled more. So if it weren't going faster here, it would eventually fall and spiral in. It's going to pick up speed. It'll be at its slowest point right over there, start sort of falling back towards it, but because it's got so much linear speed just perpendicular to that orbit, it's not going to actually fall into the sun or whatever. But it does mean that in this arc it'll be going a lot faster. So if we were on a planet like this, this month where we were closest to the sun, we would be traveling a lot faster through it. We would have a shorter month for this part. I mean, the month would be 30 days, but we'd spend a lot shorter time close to the star. As it is, what did you find for Earth's eccentricity in the first lab? 0.16. So that's close to circular. If we go back up here, the 0.1 is nearly circular. 0.5 is circular. 0.01 something? Okay, so even closer. I forget what it actually is. We are nearly circular, but not perfectly circular.
0.0167 is what it actually is.
Okay, so the 0.0167 means that we're very nearly circular with the Earth quite close to the center, but we do have a little bit of time here, and actually we are closest to the sun in January, which everybody finds surprising, but that's not really the reason for seasons anyway, which we'll talk more about. Okay, and then finally, the tough one to plot, Kepler's third law. What does Kepler's third law state? Yep, Alex.
The orbital period squared divided by the radius u is always a constant.
Right, so the orbital period squared, which we abbreviate as a capital T. Whenever you see a T like this, it means period. So a cyclical thing over r cubed is a constant. And all this says is that everything orbiting something else shares these characteristics. And so the farther out you are, the longer the period has to be, the longer your year. This is one that we will actually do some calculation on. And it won't be too bad. What I've got for you is, in the homework 6.2, is a set of distances of the 8 planets. Planet 9 is not represented here. And their average distance from the sun in AU, astronomical units, which is a unit based on the Earth-Sun distance. Earth is at 1 AU. So it's just the average distance we are from the sun. That distance is equal to, that 1 AU is Earth's distance. And we also know the period of Earth. How long does it take? 1 year. So we can use this information to describe the rest of the planet's orbits as well by this relationship. If this is equal to a constant, if we take Earth's here, we can also say that it's equal to the same thing for Mars. The radii of their orbits are given, or at least the average of their orbits. So what I want you to find out is, based on this information, how long is each other planet's year in Earth years? So just rearrange and solve all of those. Okay. Rest of today will be a work day. So if you want to spend the time now to finish up the lab, that's cool. And then we also have time to work on this. Yes, sir.
So is one side of the equation always 1 if you always use an O?
One side of if we're using Earth and astronomical units, one side will always be 1. So pretty straightforward way to figure it out. Now solving it, this will not be 1 for the R, will not be 1 for any other planet. But it's pretty straightforward solution.